appreciate your time. So my main aim is to keep you awake for the next half an hour, talking about ion mobility. So, as you probably know, there's different ways of doing ion mobility. There's linear drift tube ion mobility. There's a famous device, which is an ion mobility which can be put on the front end of the instrument. The way we do ion mobility in waters is called traveling wave ion mobility. So I thought I'd first start by explaining how we generate a traveling wave and what this wave does in order to deliver the ion mobility separation. So a traveling wave technology is based on stacked ring ion guides. So we have a series of rings here to which we apply opposite phases of radio frequencies. So the net effect of this radio frequency is to squeeze the ions at the center of the ion guide. So we have an ion beam which is going from the ion entry to the ion exit. We also supply each half of this ion guide with DC voltages. And these DC voltages are stepped between consecutive rings. So that creates what we call a traveling wave of DC potential. So this traveling wave goes all the way through our stacked ring ion guide. And obviously, because it's a wave of potential, it will have an effect on something which is charged, like our ions, peptide ions, protein ions, small molecule ions, everything. And the effect of this wave is to propel or push the ions throughout our instrument. So if we think of a traveling wave ion guide device and ions, we can see that if we push in the DC from this end to this end of the instrument, we will have a train of waves which will be moving in this direction, and our ions, which will try and sit at the bottom of these potential wells, because that is where they find the minimal potential energy. So if this happens in the vacuum, so very low pressures, as you would have in your instrument, what we're doing really is pushing the ions, but we're not really doing anything with them. However, if we do fill a traveling wave device with nitrogen at nearly atmospheric pressure, what we have is that we start getting collisions between our ions and the nitrogen gas, for instance. So these collisions will have the effect of delaying the ions as they travel through our ion mobility device. And the number of collisions that each ion will experience is obviously dependent on how big this ion is in the gas phase. So it will be dependent on its shape, size, which are ultimately dictated by the mass and the charge. So it's depending on what we call the collisional cross-section of the ion, so the shape of the ions in the gas phase. So if we bear this in mind, we can understand how a bigger ion will experience a bigger number of collisions, and therefore it will be delayed more than a small ion, which will travel through the ion mobility device much faster. And that's how we achieve ion mobility separation in our instruments by using the traveling wave technology. So the traveling wave is actually behind all of our instruments. We don't just use it for ion mobility separation, but we use it as an ion guide in the step wave ion guide. We use it in our collision cells with the TQS to improve the sensitivity of our collision cells. And obviously we use it in the SYNAPT, which is our ion mobility instrument, to introduce ion mobility separation. So just to make it easier for us to understand how we can use the SYNAPT as a platform for proteomics applications, this is the layout of the instrument. So there is a source, which is either a standard ESI source or a nanosquare source, a step wave ion guide, which again is based on traveling wave technology, and it's got the function of bringing the ions into the instrument. The instrument essentially is a Q-top, but between the quadrupole and the top, we have a tri-wave region, which is made of 3 different traveling wave cells: a trap, an ion mobility cell, and a transfer. So both trap and transfer can be used for activating ions by either CAD or ETD in the trap, or CAD in the transfer. And the ion mobility device is obviously used for inducing ion mobility separation of gas phase ions. So the fact that the ion mobility device sits in between two dissociation devices means that we can either do ion mobility of precursor ions, or we can do ion mobility of precursor ions and fragment ions, which is nice. And also because the ion mobility separation occurs in the milliseconds time scale, time-wise, that also fits nicely in between LC, which happens on the seconds time scale, and mass spec, which is on the microsecond time scale. I'll go back to the ETT towards the end of the presentation. So what do we try and get by ion mobility? So the first thing that might actually come to mind is that because you have an extra level of separation in the gas phase, you get obviously increased separation of your peptide or protein ions. Because this separation is completely orthogonal to your LC separation, because it's actually based on a chemical physical feature of your ions, which is the collisional cross-section, that obviously stretches out the features that you can identify in your sample. So we can gain in peak capacity. Because ion mobility is dependent on the collisional cross-section, which reflects the shape of the ions in the gas phase, we can start looking at structures of proteins and peptides in the gas phase. The fact that we don't just measure masses and retention time, but also drift times, which is the time that a specific ion takes to travel through the ion mobility device, means that we increase the specificity of our analysis, because we bring in another chemical physical feature. And I'll show you how we can actually use ion mobility to increase the sensitivity of our instrument for data-dependent workflows in proteomics. So, as you're probably aware, there's two main ways of acquiring data with a QTOF instrument, well, at least with our own platform for proteomics. We can either do data-dependent acquisition or data-independent acquisition. So, without dwelling too much into it, in a data-dependent acquisition, what you have is pre-selection of a defined number of precursor ions in your quad, and then these ions are induced to dissociate by either CNT or ETD in the trap or in the transfer to generate product ions. Because there is this pre-selection of precursor ions in the quad, it means that we are limited in the number of ions for which we can get structural information. And also, this analysis is in a way biased towards the most abundant peptides, because the selection of precursor ions, unless you're doing something different, is based on their intensity. So the most abundant ions will be selected for dissociation, but we might be missing out on the least abundant ions. A difference with TDA, in a data-independent acquisition, we don't have any pre-selection of precursor ions in the quadruple. So we use the quadruple purely as an ion optic device, so for transmitting ions from the source into our tri-wave region. In the transfer, what we do is we continuously cycle between a low energy scan and a high energy scan. So during the low energy scan, because we're not inducing dissociation of precursor ions, we measure the masses of these precursor ions, so we get the masses of the intact peptide. During the high energy scan, we induce dissociation of all of the ions that happen to be there at that particular time, retention time, but also drift time. So we induce dissociation and we measure the masses of fragment ions. There's no pre-selection, which means that this information is achieved for all the ions that are in the instrument at that particular time. So we can do this with or without making use of ion mobility. So if we are not making use of ion mobility, we then realign precursor ions and fragment ions based on their retention time. However, if we do use ion mobility, what we end up doing is what we call high definition data-independent acquisition. So, in this experiment, what we have is, again, we cycle the collision energy in the transfer between a low energy scan and a high energy scan. But before doing that, we have ion mobility separation of precursor ions. So what we're doing is we're sending ions to the transfer according to their drift times and retention times. Because ion mobility separation happens before the dissociation, the fragment ions that we generate in the transfer, we have exactly the same, not only retention time, but also drift time of the ions that generated them. So this means that when we go back and look at the raw data, we're not just aligning precursor and fragment ions based on retention time, but also based on drift time. So that brings in an extra level of specificity, obviously, but also what we're doing here, we're separating, ideally, not all the time, but sometimes, we might be able to separate isobaric ions, which are obviously indistinguishable from a mass spec point of view, because they might have different gas phase structures. So we are resolving what we call the chimeric aspect of sometimes some tandem mass spectra. So we're simplifying actually the analysis. So this is our data independent acquisition where we implement high mobility in our workflow. So we get qualitative information because obviously we go back and annotate the tandem mass spectra and we identify the peptide. Because we're not cycling between a survey scan and a tandem MS scan as we do in DDA, we can draw a continuous profile for a peptide which is eluting from our ELSA system. And this means that we can actually rely on this peak shape to access quantitative information as you would do, for instance, in a label-free experiment. Because we make an advantage of ion mobility, we also using the drift time as a specific feature of our ion for aiding the identification of our mass spectra. So most recently what we started doing is, so the way we used to run the collision energy in the transfer was just a linear ramp, so we would go from say 15 to 45 volts without taking into account the ion mobility of the ions that are going through the transfer. More recently we started making use of this ion mobility information to make sure that we actually use the optimal value of collision energy in the transfer. And the way we do so is based on the linear relationship which exists between mass to charge of precursor ions and collision energy required to induce dissociation of the ions, but also mass to charge of the ions and drift time of the ions. So these two relationships are both linear, which means that we can actually build a new relationships which defines the drift time, the collision energy, as a function of the drift time. So instead of having a linear gradient of collision energy in the transfer, we have a stepwise gradient of collision energy in the transfer, which makes sure that we are using the ideal collision energy for each precursor ions, which means that we don't induce small ions to overfragment, but we don't get at the same time underfragmentation of bigger ions. And that's what we call now ultra definition MS2D, so ultra definition data independent acquisition. So just to give you an idea of the proteomic workflows that we can rely on with this kind of instrument setup, if we focus on the left-hand side of this table, we have data-independent acquisition, data-dependent acquisition, which is when we pre-select precursor ions. So we have a survey scan and then we switch to an SMS and we can pre-select up to 30 precursor ions per scan. We can do what we call, in a way, that should be called really pseudo-TOF MRM, because obviously you can't do true MRM on a TOF. So it's a TOF MRM in the sense that we predefine precursor ions in the quadruple and then we use the TOF for looking for fragment ions. So we can get a gain in sensitivity because the quadruple doesn't have to scan for the entire mass range, in a similar way to what would happen on TQS. If we bring in the ion mobility elements into each of these acquisition modes, if you want, we go from data-independent acquisition to high-definition data-independent acquisition, which is what we mainly use when we look at, for instance, whole cell lysates, and we want to make sure that we are including in our analysis as many peptides as possible, so as many proteins as possible. If we do ion mobility in a data-dependent acquisition, we do what we call high-definition data-dependent acquisition, which relies on ion mobility for increasing the sensitivity of the fragment ions, and I'll show you how we do that. Similarly to HTDDA, we can do high-definition MRM if we are targeting peptides. So just to give you an idea of what ion mobility brings in when we do data-independent analysis. So this was a case study which we did in collaboration with the Karolinska Institute. They were looking at a whole cell lysate which had been spiked with SILAC peptides. So they gave us a wholesale lyset and this library of peptides which contains a total of 1,000 peptides, and they asked us to identify as many proteins as possible, as many SILAC pairs as possible, and obviously quantify as many proteins as possible based on the SILAC heavy to light ratio. So if we just look at the numbers here, we can see that when we bring the ion mobility in, we kind of double the numbers for each of the entries. So for the total number of identified peptides, for the total number of heavy identified peptides, for the number of selected SILAC pairs. So they gave us a list of 10 peptides that they were hoping to see. So we could see all of them using ion mobility, but only half of them without ion mobility. And we also doubling the number of quantifiable proteins based on the heavy to light ratio. So hopefully that gives you an idea of what the added level of separation in the gas phase brought about by ion mobility can give you in a standard data-independent analysis, if you're looking obviously at complex mixtures of peptides. When we do DDA, one of the problems that sometimes we face is that because we are using a tough instrument, the duty cycle of a tough instrument is actually limited to something between 10 and 25%. So what we hope to do when we do data-dependent analysis is to increase the sensitivity at the fragment ions level by using ion mobility. So we want to change this duty cycle from 15% to nearly 100%. And the way we do so is by using the ion mobility, which again is positioned in between the trap and the transfer, to packet fragment ions that we generate in the trap. So these fragment ions, they will have different masses, and for the same charge state, they will have obviously different retention times, which are, and drift times, which are dictated by the masses. So they will packet in the ion mobility device. We can then synchronize the release of these packets of fragment ions with the frequency of our pusher. So instead of having to push for the whole mass range all of the time, the pusher will only be pushing for that particular mass when he knows that that mass is expecting to arrive at the pusher region. So that's how we convert our duty cycle from 10–15% for a specific mass to nearly 100%. Because this synchronization between the pusher and the ion mobility is based on a calibration line that we acquire over the entire mass range of our acquisition. This increased in duty cycle is not specific for one particular mass, but is also displayed on the entire mass range of acquisition, which is why we call this wideband enhancement. So just to give you an idea of what the data looks like when we do this wideband enhancement, that's the CIT tandem MS of GluFib, which is one of the peptide standards that we use for evaluating. That's without ion mobility, and you can see that you can barely see most of the fragment ions. If we bring the ion mobility in, not quite for separating precursor ions, but for packaging fragment ions to be able to synchronize their arrival with the frequency of the pusher, we get a gain of nearly 10-fold in the signal-to-noise ratio for all of them in the entire mass range. So that's what we do when we do data-dependent analysis. We know that we have to overcome the limited duty cycle of a tough instrument, so we rely on ion mobility to do so. In terms of number of identified proteins, which is what sometimes people use to kind of appreciate the potential of an instrument, these are the numbers that we can generate. So just to give you an idea of what this kind of increased sensitivity ends up displaying in terms of results. So these are the same analysis of a wholesale lyset, different loads on column. Standard DDA, so data-dependent acquisition without any ion mobility wideband enhancement, and with ion mobility wideband enhancement. So you can see that the number of identified proteins is actually massively improved when we get this gain in the sensitivity at the level, at the fragment ions level. At the same time, we're also resolving the precursor ions in the ion mobility cell by ion mobility. So this gain is actually a combination of simplified ion population that we send to our instrument and gain in sensitivity by wideband enhancement. Something that we thought is quite interesting is obviously many people look at post-translational modifications, and many people are interested in identifying different sites of modification on the same peptide, for instance. So there might be instances when you have a phosphorylated peptide and you have more than one potential phosphorylation site. So sometimes, obviously, these peptides will be isobaric, which means that from a mass spec point of view, they will be indistinguishable. They might correlate retention time-wise, which means that you end up with a tandem mass spectrum, which is a combination of both different isomers of the same phosphorylated sequence. So in terms of pinpointing the position of the modification, that obviously doesn't help. With ion mobility, we sometimes are able to actually further separate precursor ions, even though they have very similar, obviously the same mass and very similar structure. So in this case, we were looking at ubiquitinated peptides. And we had two candidates, a linear peptide, which has the double glycine on the N terminus, and the same sequence, but with ubiquitination of the internal lysine. So they're obviously isobaric, so in this case, mass spec resolution doesn't really do anything. They had the same retention time, but luckily for us, they had slightly different drift times. So we did a high definition data dependent acquisition. And in order to be able to tell whether we were actually looking at one of these species or both of them, what we did is we extracted the drift times for the precursor ion, and you can already see that there's two different species, so this is intensity against drift time. And we then look for isomer-specific fragment ions, in this particular case B3. So B3, that particular mass could only be generated by the linear peptide, and this Y7 as well could only be generated by the linear peptide. And you can see that B3, from a drift time point of view, aligns with the species which I've labeled here as A, but not with B. So in this case, ion mobility enabled us to discriminate between the branched structure of the peptide and the linear structure of the peptide by looking at the drift time of the fragment ions which were specific for these two candidate species. So that's how we make use of ion mobility for peptide analysis. Obviously, we're also interested in proteins. Some of you may also be interested in looking at interproteins. So with interproteins, we start looking at structural features as well. So this is a typical representation on drift scope, which displays the drift time as a function of the mass to charge for a series of proteins from a standard mixture, which also includes a polymer, analyzed under non-native conditions, which means that we are unfolding these proteins, and these proteins will display a broad range of charge states. So you can see that for each of these proteins, we can actually draw a diagonal line, which goes through all of the different charge states. So by simply looking at the drift time as a function of the mass to charge, we can see where these proteins sit in this kind of two-dimensional space. But also what we can see is that in this region, for instance, there's lots of is heavily populated. Without ion mobility, that region would be very complex to look at if you try and understand what proteins you have in your mixture and how many proteins are there. So without being able to separate the drift time for isobaric ions from different proteins, we wouldn't be able to draw these lines. So we wouldn't be able to actually tell how many proteins are in this mixture. But with the ion mobility, we get different trend lines for each of these proteins, and we can actually then extrapolate this particular region, for instance, if you were interested in myoglobin, and ask the software to only give us the mass spec data for that particular region of the two-dimensional space. So we actually go from a mixture of protein to one resolved protein, which we have resolved by ion mobility without having the need to perform liquid chromatography up front. So for interprotein analysis, ion mobility does two main things. It might help you understanding the spectrum, because obviously if you have isobaric ions or ions which happens to be in the same region of your mass spectrum as your protein ions, when you're going to the deconvolution step, they might be taken into account by your deconvolution software, and that might lead to errors in the assignment of the charge state and therefore the mass of your protein. So with a star here, I labeled all of the ions that don't belong to the protein. We can very easily get rid of them by just introducing ion mobility in the experiment, and you can see that we end up with a very clean spectrum of myoglobin, which is very easy to understand, to annotate, and also to deconvolute to get the mass, the accurate mass of myoglobin in this case. Again, if we look at interproteins, another thing which is of interest is trying to start and understand what happens to these proteins when they're sprayed in the gas phase. So obviously we can either analyze proteins under native conditions when we try and preserve the native structure of our proteins, or we can try and spray them under non-native conditions and see what happens to them. Because we're still measuring the drift time, which is a function of the original cross-section, looking at how many points, if you want, on this two-dimensional map we get for the same mass-to-charge ratio, and therefore for the same charge state, might be informative as to the heterogeneity of these protein ions in the gas phase. So this is a very simple example where we have cytochrome C sprayed in the gas phase under non-native conditions, and you can see that for the high end of the mass range, we started getting separations of at least two different conformations. Here, 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 probably here as well, which have different drift times. So they're definitely different in the gas phase. So when we do things like this, we start looking into the, if you want, the structural dynamics of protein ions or other kind of ions in the gas phase, which we can then relate to the structure based on calibration of the conditional cross-section. So, as I said before, you can extrapolate that information back onto your software for data analysis. So if we were to take all of this area, which belongs to different species, and ask the software to draw a drift time versus intensity versus drift time kind of plot, what we get is this. So I've done this for different charge states of cytochrome C, so 12, 11, 10, and 9. And you can see that as we go towards lower charge states, we start getting an increased contribution from a species which has a longer drift time. So the protein is obviously behaving in a different way depending on which charge state the protein happens to be. And we can easily look at this by ion affinity. 3 minutes. Okay. So the last thing that I wanted to mention is how we do electron transfer dissociation on this platform. Without dwelling into the specifics of ETD, you're all familiar with ETD, it's just a different dissociation techniques, which sometimes is, where it's always complementary thing to CAD. Sometimes it might be better if you're looking at label post-translational modifications such as phosphorylation and glycosylation, for instance. Because what happens in ETD is that these modifications usually stay on the fragment ions. They're not lost, as it happens with CAD. So we can actually get sequence-rich tandem MS for phosphorylated and glycosylated peptides. So the way we do ETD on a CNAT is by inducing the ETD in the trap. Okay, this doesn't work anymore. But anyway, so ETD happens in the trap, so that's before ion mobility, which means that we can still do ion mobility on ETD fragment ions. And sometimes this is quite useful because if you were doing ETD of a very big peptide or an interprotein, you end up with a mass spectrum which is heavily populated by fragment ions with very different charge states. They can be easily separated by ion mobility, so we can use ion mobility to simplify ETD tandem MS and therefore ease the interpretation of the spectra. That's just a schematic of how ETD occurs in our instruments. Just to give you an idea on what we do with ETD, obviously we use ETD for sequencing peptides, we use ETD for looking at PTMs, we use ETD for looking at anything which is labeled, so for instance peptide-drug interactions or protein-drug interactions. So if you want to map the site of this interaction, sometimes you might not want to do CAD because that will mainly induce the elimination of the drug. But if you do ETD, you might be able to preserve the interaction and therefore map the site of interaction. We obviously use ETD for top-down fragmentation of interproteins as well. So just to give you an idea of what our spectra look like, so this is a spectrum of an N-glycosylated peptide taken from a digested antibody, and you can see that it's probably not very clear, but you can see that you've got all of the C and Z fragment ions that you need for being able to say that the glycosylation is on that asparagine residue and not anywhere else. Similarly, for phosphorylated peptides, Because you don't lose the phosphorylation, you will generate fragment ions, and the ones that are phosphorylated will retain the phosphorylation. So in this case, this is a nice example because we have Z5, C5 and C6 fragment ions, and the mass difference between them is exactly the mass difference of a phosphorylated grain residue. So although we have eventually other sites of modification, such as two serines towards the C end of the peptide, we're still able to pinpoint the position of modification with high confidence. That's probably it. So that's what I mentioned before. We use ETD for animal-based for simplifying, ETD mass spectra. So just to sum up, we can talk about this later. In conclusion, I hope I showed you that traveling wave biomobility can be used in many, many different ways. For proteomics applications, it's mainly for inducing an extra level of gas phase separations, which is ideal if you look at complex mixtures. We can increase the specificity of our searching processes because we bring in drift time, which is an extra feature to retention time and mass to charge. So we can increase the number of identifiable compounds, we can increase the sensitivity of our analysis in high definition data-dependent acquisition. And if we look at structural features, we can start trying to understand what happens to our peptide or protein ions when they are in the gas phase. Thanks very much for listening.